For this week 2 video, we're going to go over carbonyl group reactions, specifically focusing around carbon, nitrogen, and oxygen nucleophiles. So we're going to go over nucleophilic addition. So we're going to start with a carbonyl group and a nucleophile. So we're going to see that nucleophile attack that carbon, and that bond is going to turn into a lone pair on the oxygen. The product that we're going to get is, or I suppose I should say the intermediate that we're going to get will look just like this. And if that intermediate undergoes a proton transfer, we're going to see it be protonated by something such as water. And we're going to see that lone pair on the oxygen take that hydrogen, and that bond is going to break and go into a lone pair on the oxygen, producing a compound that looks just like this. And that just goes over a nucleophilic attack and a proton transfer. So now we're going to jump into the type of nucleophiles. So we can have carbon nucleophiles, nitrogen nucleophiles, and oxygen nucleophiles. Examples of these are acetylides, ylides, and cyanide. With carbon nucleophiles, we also see organometallic reagents and being Grignard and organolithium reagents. In nitrogen, what we're going to see is tertiary and secondary amines, along with hydrazine derivatives. With oxygen, what we're going to see are things like water, alcohols, and diols. So moving on to carbon nucleophiles, those are specifically nucleophiles. In order to be a nucleophile, carbon must have a pair of electrons that it can use to attract a nucleophile. So carbanions are an example of that, and they look like this, and there's a negative charge. Cyano, we'll see acetylide and ylides. Carbon attached, the second big part of carbon nucleophiles is that the carbon must be attached to a very low electronegative atom. And so, for example, in Grignard's reagent, we're going to see the bromine has a negative charge, magnesium has a positive charge, and this is an lithium reagent. And both of these reagents have low electronegative atoms, which make them good carbon nucleophiles. So, just for this example, we're going to see the ylide attack the carbonyl to form a betaine. So we're going to see this carbon right here attack that carbon, and we're going to see that bond break onto the oxygen lone pair. So we're going from an ylide to a ketone or an aldehyde. And then in the second step, the betaine closes to form a four-membered ring. And so what we're going to see is that produced something that looks like this. And we're just going to call this an R1 group. And so we're going to see this oxygen attack the phosphorus and close that ring. This is going to then look like this. And then we're going to see the ring collapse and produce a second phosphorus oxygen bond that's going to form. So right here, that bond is going to form, and that is the collapsing of the ring, which is going to create these two products. And that is our carbon nucleophiles, and we're gonna jump on into nitrogen nucleophiles. So this is the two different types of nitrogen nucleophiles we can have are primary amides and secondary amides. So the first part in a primary amide is going to be a nucleophilic attack of the amine followed by a protein transfer that forms an unstable carbonyl amine, I believe is what it's called. And in a part two, we're going to have an elimination of a water molecule. So it's going to be attracted. And then this oxygen is going to be deprotonated, and we're going to see the loss of H2O, and then we're also going to have a water molecule is then going to attack and deprotonate the nitrogen. And in this case right here, we also see resonance stabilization. And we're going to see this compound form. And this is going to produce in amine. With secondary amines, what we're going to see is a nucleophilic attack. So this nitrogen is going to come right there. Oxygen is going to pop off, and we have a nucleophilic attack. That hydrogen is then going to be deprotonated with the loss of a hydrogen. And we're going to see another nucleophilic attack as that oxygen goes and grabs the hydrogen. We're going to see a protein transfer as that lone pair creates a double bond, and that bond breaks with the oxygen. So we see the loss of a leaving group, specifically the loss of H2O. And then we're going to also end up doing a hydroshift, and that bond is going to create a double bond to create an amine. With oxygen nucleophiles, we're going to see the first one being water, which creates hydrates. And in an acid, the acid catalyzed hydration is typically an acid catalyzed addition to a carbonyl group, which is then followed by protonation, which followed by an addition of water, and that's going to give us a protonated product. And then deprotonation gives the hydrate. And so what we're going to see right here is we're going to see H2O plus. We're going to see that oxygen grabbed the hydrogen, and then we're going to have H2O, and that water is going to then perform a nucleophilic attack. There's a hydrogen attached to that, and that is going to cause this bond to break and to form a lone pair on the oxygen. And what we're going to see is this intermediate, and then we're going to have another H2O molecule that's going to perform a nucleophilic attack, grab a hydrogen, and that bond is going to break to a lone pair on the oxygen. And we're just going to fill this out. And this is the product that we're going to see along with H3O+. So that first step is a protonation. The second step, we're adding water. And the third step, we see a deprotonation, which then forms our hydrate product. In a base, the base catalyzed hydration is an example of base catalyzed addition to a carbonyl group, and a strong nucleophile is added and then protonated that produces a hydrate. So what we're going to see is we're going to use a hydroxide ion, and we're going to see that attack that carbon, bond breaks, lone pairs go into oxygen. We're going to see this alcohol, and what we're going to see is another nucleophilic attack on a water molecule. And you're going to see that oxygen grab the hydrogen, that bond's going to break. And we are going to get these two as our product. So the first thing we see is a hydroxide is added, and then we see a protonation. The second type of nucleophile is, or not nucleophile, the second example of an oxygen nucleophile is an alcohol. And in this case, we're going to see a protonation of a carbonyl oxygen. And so we're going to see that oxygen grab that hydrogen, and that lone pair is going to break onto the A group. We're then going to see this bond break. So a lone pair is going to jump onto that oxygen, and then this is where we see our resonance stabilized cation. And that's pretty simple. The next step for this same reaction is when we see a nucleophilic attack. So we're going to see this nucleophile attack that positive charged cation, and what we're then going to see is this A group is then going to deprotonate that group, and that bond is going to turn into the lone pair on the oxygen. And that is how we are going to get the, this is just a result of an addition of a hydrogen and an OR group to a carbonyl group. The next example of oxygen nucleophiles are diols. And what we're going to see is a protonation of the OH group, followed by the loss of a water ion. So first we're going to see deprotonation, and then we're going to see the loss of a water, and then we're going to see some resonance stabilized cation. That cation is also going to go under nucleophilic attack, followed by deprotonation, which creates an acetyl. So we're going to see nucleophilic attack, a deprotonation, and then this is the product that is formed. And that just covers up week 2. I hope this is helpful.